Welcome to our video on special differential equation solving techniques. Today we'll focus on two important methods, integrating factors and homogeneous equations. Let's start by understanding what these techniques are used for and how they can help us solve differential equations that might otherwise be difficult to approach. Let's begin with integrating factors. An exact differential equation has the form mu of x times m times dx plus mu of x times n times dy equals 0. When a differential equation is in exact form, it becomes much easier to solve because we can express it as the differential of some function. But what if our equation isn't initially in exact form? That's where integrating factors come in. An integrating factor is a function mu that, when multiplied through our equation, transforms it into an exact equation. Let's look at our first case for finding an integrating factor. If the expression, the partial derivative of m with respect to y minus the partial derivative of n with respect to x, all divided by n, depends only on x, then the integrating factor mu of x equals the exponential of the integral of this expression with respect to x. This gives us a function mu that depends only on x. Similarly, we have a second case. If the expression, the partial derivative of n with respect to x minus the partial derivative of m with respect to y, all divided by m, depends only on y, then the integrating factor mu of y equals the exponential of the integral of this expression with respect to y. In this case, we get an integrating factor that depends only on y. Let's work through an example to see how integrating factors are applied. Consider the differential equation, x times dy over dx plus 2, y equals e to the power of x. First, we'll rearrange into standard form x dy minus 2 y dx equals e to the power of x times dx. Comparing with our general form, m dx plus n dy equals 0, we have m equals negative 2y minus e to the power of x, and n equals x. Now we check if either of our conditions for an integrating factor applies. Let's compute the partial derivative of m with respect to y, which is negative 2, and the partial derivative of n with respect to x, which is 1. So the expression del m slash del y del n slash del x slash n equals minus 2 to 1 slash x equals dash 3 slash x, which depends only on x. Therefore, we can find mu x equals exp integral dash 3 slash x dx equals exp dash 3 ln x equals exp ln x caret minus 3 equals x caret minus 3 equals 1 slash x caret 3. Multiplying our original equation by this integrating factor, 1 slash x caret 3 times x dy, 2y dx equals e to the power of x dx, gives us 1 slash x caret 2 dy, 2 slash x caret 3. Y dx equals e caret x slash x caret 3. Dx, we can verify this is now exact, and then solve using techniques for exact equations. Now, let's move on to our second technique, homogeneous differential equations. A differential equation is homogeneous if it can be written in the form dy over dx equals g of y divided by x. The key property of function g is that it's homogeneous of degree 0, meaning g, ky, kx equals g, y, x for any non-zero constant k. To solve a homogeneous differential equation, we use the substitution v equals y divided by x. This means y equals v times x. Differentiating with respect to x, we get dy over dx equals v plus x times dv over dx. Now, substituting these into our original equation, v plus x times dv over dx equals g of v. Rearranging x times dv over dx equals g of v minus v. This is now a separable equation in variables v and x. Let's work through an example of solving a homogeneous differential equation. Consider the equation dy over dx equals x squared plus y squared divided by xy. First, let's verify this is homogeneous. If we replace x with kx and y with ky, gkx ky equals kx caret 2 plus ky caret 2 forward slash kx ky equals k caret 2 x squared plus y squared forward slash k squared xy equals x squared plus y squared forward slash xy equals gxy. So g is homogeneous of degree 0, and we can use our substitution method. Let v equals y slash x. So y equals vx and dy slash dx equals v plus x dv slash dx. Substituting into our original equation, v plus x dv slash dx equals x squared plus v caret 2x caret 2 forward slash vx caret 2 equals 1 plus v squared slash v rearranging x dv slash dx equals 1 plus v squared slash v equals 1 plus v squared minus v squared slash v equals 1 slash v. This gives us the separable equation. V dv equals dx slash x integrating both sides. Integral v dv equals integral dx slash xv caret 2 slash 2 equals ln x plus c. Finally, substituting back, v equals y slash x caret 2 slash 2 equals ln x plus c, y squared equals 2x caret 2 ln x plus c. And this is our general solution to the original homogeneous differential equation. Now, let's discuss a related technique. For equations of the form dy over dx equals g, x plus by, we can apply the substitution z equals x plus by. Then, dz over dx equals a plus b times dy over dx. Rearranging for dy over dx equals dz over dx minus a divided by b. Substituting into our original equation, dz over dx minus a divided by b equals gz. Rearranging, dz over dx equals a plus b times gz. This is a separable equation in variables z and x. Dz over a plus b times gz equals dx. After solving for z in terms of x, we substitute back to find y using y equals z minus x divided by b. Let's conclude with an example of this alternate form. Consider the equation dy over dx equals 3x plus 2y squared. Comparing with our form dy slash dx equals g, x plus by, we have a equals 3, b equals 2, and g, z equals c squared. We apply the substitution z equals 3x plus 2y. Then dz slash dx equals 3 plus 2 dy slash dx. Solving for dy slash dx equals dz slash dx 3 slash 2. Substituting into our original equation, dz slash dx 3 slash 2 equals z squared. Rearranging, dz slash dx equals 3 plus 2z squared. This gives us the separable equation, dz slash 3 plus 2z squared equals dx integrating both sides. Integral dz slash 3 plus 2z squared equals integral dx using the standard integral form, 1 slash square root 6. Arctan z square root 2/3 equals x plus c. Solving for z equals square root 3 halves tan square root 6 x plus c. Finally, substituting back to find y equals c3x slash 2 equals square root 3 halves tan square root 6 x plus c. 3x slash 2. To summarize what we've learned, for differential equations that aren't exact, integrating factors can transform them into exact equations, making them easier to solve. We can find an integrating factor mu x or mu y using specific formulas when certain conditions are met. Homogeneous differential equations of the form dy slash dx equals g, y slash x can be solved using the substitution v equals y slash x. And equations of the form dy slash dx equals g, x plus by can be solved using the substitution z equals x plus by. Both techniques rely on clever substitutions that transform complicated equations into simpler, separable ones. Practice with these methods will help you recognize when to apply them to solve differential equations efficiently.